Hello children, we are studying rational and irrational numbers. Today we shall see how to express a recurring decimal in P upon Q form. Earlier we have studied that all rational numbers can be expressed in the form P upon Q, and the decimal representation of a rational number is either recurring or a terminating decimal. Right from lower classes you have studied how to express the terminating decimals into the form P upon Q. That is simply by adding some powers of 10 in the denominator depending upon the number of decimal places. I hope you know it. So we shall see here basically that how to express a recurring decimal into the form P upon Q, because that recurring digit makes a problem to express it in the fractional form. So first case I will take here 0.39. okay, 0.39 recurring. You all know how to read it. This means the recurring part is 3939 set of digits will keep on recurring. So first thing in this part, what you have to do is assume let x is equal to your 0.39. Now this, what is the meaning of the 0.39 recurring? 0.3939 keeps on repeating. In case you forget to write this part, it shall become a terminating decimal. That will be wrong, so be careful. Now the step is what you have to just check out. Here integral part is 0. How many digits are repeating here? 2. So multiply this x by 10's power 2, that is 100. 100x. X becomes 100x. So when you multiply this number 0.39 recurring there by 100, what will happen? This decimal would shift 2 places to the right. You may remember multiplication means increasing the number. So what shall it become? 39.3939 recurring. In both the cases, you can also write, see the way of writing. You may also write x, which we have assumed as 0.39. If you don't want to write these dots, you have to write this bar. Okay, and so 100x is equal to 39.39 recurring. Any of the two ways you may use. Now what is the further part? This, if let it be statement 1, let this be statement 2. Then from this statement 2 you subtract statement 1. So what will you have? Write it one below the other properly. 100x, which is equal to 39.39 minus x, that is equal to 0.39 recurring here, and subtract. So what do you have here? 99x is equal to, see why we have done all these parts. Now this recurring part gets fully cancelled here, right? So your answer is what left here? 39. This is the purpose of doing all these things. So x equals 39 upon 99. So first thing, which if you had a doubt that 39 keeps on repeating, how will we write? We have written it into the P upon Q form, number 1. So it proves otherwise that the rational number can be expressed into the form of a recurring decimal as well. Second important thing what you have to remember, we have always studied that when we write into the form P upon Q, then P and Q are in the this P upon Q is in the simplest form. That is, there is no common factor between P and Q. So if you can simplify, you need to simplify it. So by 3 you can simplify it. 13 3s are 39 and this gets 33. So what's the answer? 13 upon 33. So how would you write the answer here is, what was x? X was 0.39 recurring, which is written as 13 upon 33. Answer 1. Let's see the second example here. 2.3 recurring. Okay, what is the meaning of this? 2.3 keeps on repeating itself. Here also what I have to check is, first thing I will be writing here, let this I will be, for our simplification we will do x is equal to 2.3 recurring. Now check out how many digits are repeating here, only 1. So you will multiply both sides of this equation by 10. So you have 10x is equal to, multiplying 2.3 recurring here by 10. What will happen to the decimal? Decimal shifts how many places? 1 to the right. So what does it become? 23.3 keeps on repeating. So I'll write it in this form. Hope you all have understood. Again I shall subtract. So I'll show you in short now. 10x minus x. What is the answer here? 9x. Right? And 23.3 recurring minus 2.3 recurring. So 3 recurring parts gets cancelled. 23 minus 2, that comes as 21. Therefore, I know that you all have done it. So as a revision I am taking it. 9. 3 7s are, again you cannot leave the answer is 21 upon 9. 3, what's the answer? X equals 7 upon 3. And what was x? 2.3 recurring equals 7 upon 3 is your answer, right? Look at the next third example. 0.3 105 recurring. Now here the period is 105, right? 3 is not getting recurred here. So we need to do a special trick for that. We can do all this elimination very easily, children, when the right hand side contains only the recurring part. So first purpose is eliminate this 3. Very simple. How would you do? Multiplied by 10. 10x by 10x, because only one digit I want to shift to the left. So what it will become? 3.105. The numbers next to the, the digits next to the decimal are recurring. Now one more set I want. Yeah, one more statement I want, where only again the recurring part appears. So how many digits I have to shift this decimal? 3. So multiplied by 10 raised to 3, multiplied by 1000. Okay, for our sake I will name it as 1. Multiplying both sides of the statement by 1000, I get 10,000. X equals 3105. Decimal shifted 3 places to the right. It becomes as 105 recurring. Let me name it as statement 2. Then what I'll do? Statement 2 minus statement 1 I'll do. Elimination is easy now. So I just got 10,000 x equals 3105 minus 105 recurring minus 10x is equal to 3.105 recurring. Subtract. So what do we get here is 9990x is equal to 3102. This part is eliminated here. That was our purpose. So x is equal to 3102 divided by 9990. We can of course simplify it, right? So we need to work out with that. In the simplest form we have to write. So 2 1s are 5s are 5s are and 1 upon 2 4s are 9s are 9 and 5. Can it be further simplified? Yes. You can use the divisibility test, no? So 6 plus 6 12 divisible by 3, and this is 27, that is also divisible by 3. So we will divide it by 3 again. 3 5s are 1 7, and this will be 3 1s are 6 are 18, 6 are 18 and 3 5s are 15. So what do you get on simplification is 517 upon 1665. Don't forget to write the answer. What was our x? 0.3105 recurring equals 517 upon 1665. I hope you all understood this. Now see one more, the next example, the last example. 4.321 is recurring here. What is the difference here? The integral part in this question was what? 0. Here we have got 4, right? Statement 1, x is equal to, assume it equal to x, 4.321 recurring. You want to shift this 3 to the left of the decimal, so, or you want to shift the decimal to the right, so you will multiply it by 10, only one digit. 10x equals 43.21 recurring. Now you wish to shift it how many places? 2 places to the right. So statement 1 should be multiplied by 100. So LHS will be what? 10 into 100, that is 1000x is equal to 4 3 decimal shifts there, 2 1 recurring part still left, this statement 2. From the statement 2 you are going to subtract. So 1000x equal 4321.21 recurring minus, what are we subtracting? First statement, right? 10x is equal to 43.21 recurring here. Subtract, what this will be? 1000 minus 10 is 990x. 21 recurring part gets cancelled. 11 minus 3, that is 8. 11 minus 4 is 7. This becomes 2 and this is 4. Right? Therefore, x is equal to, here I'll write so that simplification I will be able to show. 4278 divided by 990. Dividing by 2, we get 2 2s are, 1s are, 3s are and 9s are. And this is 2 4s are 8, 2 9s are, 2 5s are. Can it be further worked out? Yes, by divisible by 3. This is also divisible by 3. So go, proceed. 3 7s are 21, 1s are, 3s are. 3 1s are, 6s are, 5s are. Final fraction is what? 713 upon 165. So what is your answer? 4.321. 321 recurring is equal to 713 upon 165. Hope you have understood. Now let us see what are irrational numbers. So far we have studied what are rational number, which all sets it includes. Okay, we studied that rational numbers are the numbers which can be expressed in the form P upon Q. Okay, now what if we find some numbers which cannot be expressed in the form P upon Q, binding the condition that P and Q are integers and Q is not equal to 0. There exist some numbers which cannot be expressed in the form P upon Q. Okay, and if you check its decimal representation, you find that it is neither terminating nor recurring. I hope the point is clear to you. Rational numbers which can be expressed in the form P upon Q, decimal representation is terminating or recurring, whereas the numbers which cannot be written into the form P upon Q and the decimal representation is neither terminating nor recurring, they are called as irrational numbers. Example, under root 2. It's a very familiar number to you. Okay, if you try to find the square root of 2, you might have tried also using division method in standard 8. You will find that it neither gets ended up nor any group of digits start recurring. It just keeps on extending. Same is the case of under root 3 also. The decimal representation is not getting terminated nor it is recurring. Okay, so these kind of numbers are known as irrational numbers, and as we denote the set of rational numbers by Q, hence the set of irrational numbers is denoted by Q dash. That is the complement of rational numbers. That means either the number will be a rational number or it will be an irrational number. And if we find the union of these two sets, rational numbers and irrational numbers, if you find the union, set language you know, then we shall get a new set. It is known as the set of real numbers. So how do you define the set of real number? It is a set of all x such that x is either rational or it is irrational. Let's summarize here. Set of real numbers denoted by capital R. We are talking about real numbers is the union of Q and Q dash. What is Q? Rational numbers. What is Q dash? Irrational numbers. What are rational numbers? Which can be written into the form P upon Q. Right? What are irrational numbers? Which cannot be written into the form P upon Q, and the decimal representation is neither terminating nor recurring. Here decimal representation is either terminating or recurring. Okay, and P upon Q format. Again, as in the previous video I explained, rational numbers we can further have the union of two sets, integers and non-integral rational numbers. Integers part, you know, this is set of integers, and the non-integral part, that is the rationals in between the two integers, this part. Again, integers we can subdivide into two parts, set of negative integers, and one clear part you can have whole numbers. Okay, so integers and whole numbers together go to integers. Whole numbers, again we can have the union of two sets, 0 with a set of natural numbers. So concluding, if this is a set of natural number, if 0 is included in that, we get a new set, that is of whole numbers. Whole numbers combined with the opposite or the negative integers give us the set of integers. Integers and non-integral rational numbers together gives us the set of rational numbers. Rational numbers and irrational numbers together give us the set of real numbers. Hope you have understood this concept well. Keep it in your mind. It will help you a lot understanding the number system. Thank you.